5 grams of vanadium metal reacts with oxygen gas to give 2.679 grams of vanadium oxide. What is the empirical formula of the product? So our empirical formula will have vanadium and it will have oxygen. There will be some mole amount of vanadium, there will be some mole amount of oxygen. The trick is to figure out what those mole values are. Okay, so we can go back to the question. It says 1.5 grams of vanadium. Well, if I want to get the moles of vanadium, and I'm given 1.5 with a ridiculous amount of sig figs grams of vanadium, how can I convert the grams into moles? The molar mass. Grams of vanadium into moles of vanadium. That number comes from periodic table. 50 something. I don't know why I still can't see it.
I know, I'm so sorry.
Oh, yeah, element 23. Okay, and that would get us a mole value. Anybody with a calculator who has already calculated it? 0.0. Okay. The next part, we also need to know the moles of oxygen. What are we given to start with? Is that going to be our 2.679 grams? Why not? That's the vanadium oxide. Okay. So what this problem is relying on is that you know if we take vanadium plus oxygen to produce vanadium oxide, that if I know the mass of 1 and I know the mass of the vanadium oxide, I know the mass of the oxygen to be 2. Conservation of mass. Okay. Was the mass of vanadium actually 1? No. What was it? 1.5. What was the mass of the vanadium oxide? I would go through and solve for O. The mass of my oxygen will be 2.679. Oof, sorry. 79 minus 1.5. Look at that. I can do long subtraction. It's supposed to be kind of funny. So 1.179 grams of oxygen. I need to get into moles of oxygen. How do I do that? Convert to moles using our periodic table. 1 mole is 16. Why are we not doing 13? Or not 13, sorry. 32.
Oh, okay.
We're looking at atoms here. We aren't looking at a molecule of oxygen produced. This is going to be atoms. So we're going to be sticking to that 16. What does that give us for a number? 0.073 moles of oxygen, which then means I could write out my empirical formula as vanadium 0.029446, oxygen 0.073. Does that look reasonable? No. So what did I tell you to do? Divide by the smallest number. Which is the smaller number, 0.02 or 0.07? Okay, 0.02. So I divide them both by the 0.029446. And just because I know colleagues flip out at this, I'll point this out in a second too. 29446. First one equals 1. Yay! Moles of vanadium. The next one equals 2.5 what? 2 moles of oxygen. Okay. So our formula would be Vanadium 1, oxygen 2.52. Can I have a half of an oxygen? No. So what do I have to do? I'll come back to that in a second. I'll multiply everything through by 2, and my formula becomes V2O5. Okay. There's a question on the 2.52. You took 0.073 divided by 0.029446.
I ended up with 2.479.
The 2.479 is fine. Which is ultimately going to come out to 2.5 anyway. The reason we have that difference there is I'm going to bet, because Melissa, you said the 2.52, right?
Yeah.
Yeah. You probably didn't divide by 0.029446?
No, I just did 0.029.
Yeah. So she did a round. Technically wrong. You shouldn't round. How much of a difference is it going to make? Not a big difference, so we don't worry about it. Okay. This is one of the reasons why I tend to get sloppy when I go through do my calculations as well. Particularly on a multiple choice, I can reason my way through those rounding errors. Okay. So when we talked about this before, getting our empirical formula, the first one we solved, we had whole numbers outright. Okay. The one issue is sometimes we won't get whole numbers outright, but we need to multiply by whatever gets me closest to that whole number. Okay. To get 2.52 close to a whole number, I multiply by 2 and I got 5. Okay. Could I have multiplied by 3 or 4 or 5 or 6 or any one of those? Yes. And in the process of that scale up, does that result in the reduced ratio? And you'd find out no. Okay. Multiplying by 2 was the only one that gave you the smallest whole number values.
Do you always multiply?
Nope. If we came out with 2.3, right, you'd be multiplying by 3. And you got that because 0.3 is the same as 1 over 3. Okay. So for the sake of this class, in fact, I think with this question, it was an accident because I usually want them to come out as whole numbers. Cat's out of the bag, it's already there, so we just had to work with it. Yes, James?
How do you know when to use oxygen atoms when the problem requests oxygen gas?
It comes down to where we're calculating that value out. Okay. We know the mass of oxygen that came out of that. Okay. Whether it was O2 or O, we know the mass was that 1.79 grams. So it's easiest just to call that O. Yeah.
So when you're dividing the 0.029446, there's no unit on that, or
There is not a unit associated with it because it's technically a unit conversion. You're converting between those two, and you could bring in a whole bunch of extra units. Don't worry about the units here. Just divide it through by the
that's
smallest
why it's
number.
not like the bottom, because that's why I was confused, where it would be oxygen and values for
Vanadium.
okay.
Yeah. Don't worry about the unit conversion there. Any other questions? Yeah.
Could you explain again why you multiplied by 2 there at the end?
If we did not multiply by 2, how many oxygens do you have? Can you have half an oxygen?
No.
No. So the decision on how we got it to be by 2 is that what happens if we took 2.5 and turn it into a fraction? What is the fraction value for 2.5?
2 and 1/2.
That's not a fraction, that has a number in front of it. 5 halves. How do you get rid of the half? You get rid of the half by dividing by 2. You multiply by 2. Denominator, numerator. Why do we multiply by 2? It canceled. Okay. So when you run into cases where you have to scale it higher, you're scaling it higher because the value that you're getting comes out exactly at a half. exactly at a numerically easy value to do. So half is super common, a third is super common. Okay, 0.333 or 0.5.
Third, then you
Multiply by 3. Okay? I just want to call your attention to it. Something relatively minor here. You will find people freak out at these equal signs. Why would anybody freak out at that equal sign?
Because you're making an approximation. Just add it
Is 1.179 divided by 16 equal to 2.479? No. So putting the equals in stacked like that is saying everything equals something all the way through. Mathematically, no, it's not. You should be doing it as a separate step. Okay? Such a small effect in how you organize your work. Some people really, really care about that. Some people don't. I don't. Others do. Okay? So since you may encounter others, I want you to be aware of that. That putting that in as an equality all the way across is technically wrong because you're adding in calculations that don't equal each other. Okay? If it doesn't make sense to you, don't worry about it. Hopefully the person that does care will yell at you for it then, and then it'll become more apparent. Make sense? Ish? Okay. Next question. If you don't mind, I'm just going to sit back here for this one. 1 mole. Even if you did mind, I was going to sit back here. 1 mole equal, that's probably not true, 22.4 liters. When is that statement valid? It has to be a gas at STP. What did ST stand for? Standard temperature. What is standard temperature? 0 degrees Celsius. 0 degrees Kelvin means nothing exists. It's a bit of a problem. That's our absolute zero. So it's 0 degrees Celsius, or if you wanted to convert it into Kelvin, 273 Kelvin. Standard, or SP, stands for standard pressure, and our standard pressure is 1 atm. So as far as our answers go, we have 1 atm, the species is a gas, both of those are true, 0 degrees Celsius, A, answers A, B, and C. Are there questions on that one? No? Okay. I'm going to erase all that. And then I heard 21. 21's a little bit more on just kind of the facts on what's going on with this. We're looking for not true about ideal gases. Okay, so something to watch out for. It says not. Okay. I do try to call attention to the negatives. That doesn't always happen, particularly in standardized tests. They usually don't call attention to it because they're trying to trick you. Okay. I am sort of trying to trick you, but I'm trying to do it in a nice way. Okay. So, not true about ideal gases. Gas particles have no volume. Okay. For an ideal gas, that is our number one assumption. Okay. We say that they have no volume. Which is kind of a weird statement because do objects have volume? Yes. So it might seem like a very odd thing to assume, but if you consider gas, the particles are so far away from each other that when you put in one particle, it's not really decreasing the volume by much. If you put in a second particle, it still has access to the whole container except for the exact one location, but the odds that it's ever going to get to that exact same one location is so slim that we don't worry about it. So that statement is actually true. Gas particles have no attraction for one another. It's also true. Okay? If they have an attraction for one another, it complicates things. Okay? Just think about life. No attraction to anybody, there wouldn't be a big deal. As soon as you get an attraction between one person and another, well, that other person has to be attracted to you too. Otherwise, it just sucks. Okay? So, gas particles, we assume no attraction. Gas particles collide without losing energy. Also true. Okay. Gas particles move in random straight directions. True. What's going to be easier to model? Somebody running in a straight line or somebody running all over the place? Straight line. What we're trying to do is model a real system. Okay. So we're going to pick the simplest possible option that we can. Gas particles move less at higher temperature. Okay. That one is actually false. As you add heat, what happens to your particles? They move more. They have more kinetic energy. That statement is wrong. Okay? That's an easy way to change that statement. And since I haven't written the exam, that may not be a bad way to do it. Okay? We tend to associate moving with temperature. But I could just as easily change this question to now gas particles have more kinetic energy at higher temperatures. Is that one true or false? That's true. And now you wouldn't be able to answer the question because they were all true. Okay? So I'd have to go through and make that say less kinetic energy. Make sense? Okay. I actually kind of like that change. That might show up. Other questions? What? 23. To increase the amount of dissolved gases in a liquid, so what am I doing? I'm taking a gas and I'm making it a liquid. Am I answering the wrong one? No, that's right. Okay. Gas, turning it into a liquid. Okay. I should blank the temperature and blank the pressure. How do I get a gas to turn into a liquid? I cool it down. I remove heat from it, which would mean the temperature drops. So what should I do to the temperature? Decrease. A is wrong. D is wrong. E is wrong. Go figure. In a multiple choice, both the next options were available. Okay, but at least based off of that, you've narrowed it down to a 50-50. Okay? Because now we move into the pressure, and I would argue the pressure is a harder one to work with. Okay? What do we do with the pressure? What do you think?
The pressure on certain gases, when you put pressure on it, it turns it into a liquid, which is the atom.
If we increase the pressure, what's happening? We're making sure they can't move as much. Oh, well, liquid can't move as much. So if I increase the pressure, I'm now making it more like a liquid. So I want to increase the pressure. The answer that decreases the temperature and increases the pressure, B. Okay. Notice again, even in solving this, I crossed answers out. As soon as I have an idea, I'm starting to work through and eliminate things. Don't just look at it and think, oh, well, it's this and then this. Because you'll say, oh, it's increase and then decrease. Or decrease and then increase. Oh, well, I see D increases and decreases. Why is that not the answer? Because it wasn't in the right order. Okay? So by eliminating your answers, as silly as it may seem to write that extra stuff down and that it may take time, it can improve your odds of getting the question right and getting less things confused. Okay, so please write stuff down. Okay. And I'll just address it just because. Usually the response I get from students, but there's not enough time. I think every test, there's maybe 2 or 3 people that have stayed the full time. Okay. So right now, yeah, there is enough time. You could write down, you could probably copy the test, verbatim, question by question, 2 or 3 times in the amount of time you have to take the exam. Okay? There is enough time to write stuff down. Write it down. Okay? Next question. Is that in there? I think I can squeeze that in there. Yeah, let's do it. 25. Sample of neon gas at 1.2 atmospheres compresses from 0.25 liters to 0.125 liters. If the temperature remains constant, what is the final pressure in ATMs? Okay. This is a gas law question, and within the gas laws there's a couple approaches. One, you've memorized all your individual pieces of the gas law. Charles' law, Gay-Lussac's law, Avogadro's law. Okay? I haven't memorized any of those. There's only one expression I've memorized, and that is R equals PV over NT. Okay? How is that going to be relevant here? Well, I'm looking at an initial condition and a final condition. What am I given initially? Giving the pressure at 1.20 ATMs. What else am I given? The volume. What is the volume initially? 0.25 liters. That becomes tricky because you have to be able to interpret the English out of that statement. It started at 0.25 and went to 0.125. Okay? In my expression, I also have N and T. Am I told what the moles are? No. So I'll just call that N sub I. I for initial. Temperature. What am I given for temperature? I wasn't given a temperature, so I'll call that T sub I. I then also have my final conditions. What is my pressure given finally? I don't have it. That's actually what I'm solving for. Okay. What is my volume? 0.125 liters. What is my moles? So don't know is actually kind of questionable. I do actually know. It's the same as what I started with. I took a sample of gas and I changed the volume and the pressure. I didn't change the amount of gas. It's the original sample of gas. So my moles final are my moles initial. Okay. What is my temperature final? It's constant, which means my temperature final is my temperature initial. This is where the ideal gas law comes into play. At initial, what is R? The same value as it is final, which means I can take my pressure initial, 1.20, was that right? Why am I freaking out at that number? 1.20 ATMs times my volume. What was my volume initially? 0.250 liters. Okay. What were my moles? N sub I. Okay. What was my temperature? T sub I. I know this equals then my final conditions. My final conditions, it's the pressure. I don't know the pressure, so I'll put P for pressure. I'm really creative. Volume. What was my volume? 0.125 liters. What was my moles? N sub I. My temperature? T sub I. What happens?
The bonds cancel out? No, they don't.
Yes, they do.
Did it?
The moles are exactly the same on both sides of the equation. They cancel. Temperatures are the same on both sides of the equation. They cancel.
I was hoping.
As long as they're the same, they can cancel out. What can I now do? My 1.20 ATMs times our 0.250 liters divided by 0.125 liters And I now have my pressure.
So the liters cancel out.
So then what happens? The units of liters cancel out. Ooh, they canceled. Is that a good thing? If I run the calculation, what unit would I be left with? ATM. What's the unit for pressure? ATM. So there it is. Now I can just punch it into the calculator and I can get my answer. And the answer becomes 2.4. Justin, was it you I was talking with on that one? So one of the possibilities, what's that? What? I was talking with somebody about this. We said, oh, well, it just changed by a factor of 2. So I'm just going to multiply by 2. Okay. Changed by a factor of 2. So I'm just going to divide by 2. Why did you multiply or divide by 2? You did that because of all of this work. That's how you could decide if you need to multiply or divide by 2. So just looking at the numbers and saying, oh, there's a change by a factor of 2, I'm just going to multiply by 2. Well, you could have just as easily said, well, I'm going to divide by 2. You have to know why you're doing it. The why is going back to the relationships between those. And I believe when I was talking with whoever it was about this, they went through and said, well, because it changed by 2, it went down by 2. I want to change that to down by 2, and they came up with the answer A, which happens to be the wrong answer. Just because it decreased by 2 here doesn't mean your answer is going to decrease by 2. It could also increase by 2. That's why we have the expressions. Make sense? Yes?
Also, I mean, it says the 1.2 ATM capacitors, so wouldn't the pressure be greater if the volume was smaller?
So there's another approach to this that works out almost perfectly for this question, and not perfectly because of answer E throwing a monkey wrench into this. Okay? If you remember the individual relationships, if you have that spatial awareness, you've worked with gases before or just blown up a balloon. Okay? If we compress the volume gets smaller, what happens to the pressure? It increases. Okay? Well, just based off of that observation, is A right? No. Is B right? Is C right? No calculations and you're down to 50-50. Okay? Arguably, if you understand your relationships really well, you would probably see that it needs to double. And you could then say your answer was D, and not E, none of the above. So there's multiple ways to go through and approach it. What I've shown you here is the hardcore, just mathematics, number crunch the crap out of it. Okay? We could also go through and kind of process our way through. The processing our way through doesn't get us to the final answer. We still have to number crunch, but it gets us darn close. Okay? Thank you for that observation. Make sense? Questions there? You're fine. Which of the following conditions would increase the pressure measured of an ideal gas? Okay. This is where, again, I would go back to the ideal gas law. You could go through and reason your way through the bits and pieces of it. Okay, but what I said I remembered, I actually memorized Pivner, not the R equals, but PV equals nRT. So pressure equals nRT over volume. Okay, so let's start. Decrease the length. Is length a measure of moles? Temperature? Volume? No. What is decrease the length? The wrong answer. Okay? It doesn't make sense. There's not enough context within changing the length to do anything to our pressure. It's there because I needed an extra answer. Okay? Moles. Moles does show up in our answer, or in our equation. If we increase the moles, if I make n a bigger number, what happens to the pressure? Pressure gets bigger. Oh, interesting. Guess what? That kind of seems like the answer. Okay. If you got time, go back and check. Increase the volume. What happens if I increase the volume? Okay. Because the volume is in the denominator, if I make the denominator bigger, the pressure is going to decrease. Well, I wanted to increase the pressure, so that answer is wrong.
Why would it be multiplying to get
So
each
let's
other?
try it this way. Do you trust the equation? Yes. Okay. So pressure equals nRT, we'll leave all the same. Let's just for the sake of it, mathematical mumbo jumbo, and they came out to be 1. Nice. Volume changed. I'm going to say mathematical mumbo jumbo, volume is 1. What is my pressure? New conditions where I have now increased the volume. Okay. I'm not changing nRT, so my numerator should be 1. But I've now changed my volume. I've increased the volume. Let's make sure it's a good increase. Let's go to 100. What's the answer? What happened to the pressure? It went down. I think I did that wrong. What happened to the pressure? It went down. Okay. So you can go through and simplify some approximations and just do some random subs, particularly when it's increase or decrease. Anytime you're asked for something like that, pick a really small value and a really big value. Look at a big extreme. Notice I didn't pick 1 and 1.01 because those numbers are too close to each other to help me see that, so I picked numbers as far apart as possible. Okay. Decrease the mass. This one's actually kind of tricky, so I want you to think about this a little bit. Does mass show up in my equation? Well, kind of how? The moles. I can convert mass into moles. I could come up with an ideal gas expression, okay, where grams is involved in it, okay, by doing a conversion through moles. Okay. But if I decrease the mass, what am I doing to the moles? I'd be decreasing the moles, which would be decreasing the pressure, which isn't what we want. So while the mass doesn't directly show up, it could theoretically translate into it. You have to recognize where you can get your different measurements from the values within that. Decrease the temperature. If you decrease the temperature, your numerator gets smaller, which then means your pressure gets smaller as well. Only one answer works, increase the moles.
Why does the increasing of the moles work again?
Look at our expression.
Right.
If n gets bigger and t and v stay constant, what happens to p? The pressure must go up. We don't have a choice. If that value gets bigger, so we can do the same kind of, stupid lines. Same kind of thing we did before. Pressure equals moles. Let's pick a mole value, 1. R times T we'll say is 1. Volume, we're just going to pick 1 liter, 1. If I increase the moles, instead of it being 1, let's make it 100. R and T comes out to 1. Volume was 1. Our value is 100. What happened to the pressure? It increased. So you can do those kind of random subs in just to see what happens. Make sense? Next. We're going to need a balanced equation to start this off. Okay. Sodium carbonate mixed with water, mixed with carbon dioxide to produce sodium, I don't like that N, sodium hydrogen carbonate. Okay. We are making one assumption right here, or at least I did when I made this question, that you know how to make this equation. and for some reason you were like, oh, I don't remember how to do this, you could raise your hand, and I'd be like, it's a combination reaction. And I would leave you with that. Okay? Then you have all the context that you need to figure out the equation. Okay? So we do need an equation. Okay? What's that?
Make sure it's balanced.
We need to make sure the equation is balanced. Okay? Is the equation balanced? No, we'll probably actually have a really hard time balancing this equation. Why is that? When you write down your formulas, you better make sure your formulas are correct. You're still responsible for the nomenclature from Unit 2. Okay? What is the charge on sodium? What is the charge on carbonate? Is that formula correct? Nope. We need 2 sodiums to balance out the carbonate. Is the formula for water correct? Formula for CO2 correct? Sodium hydrogen carbonate? Yes. Now you can balance the whole thing. Does it balance just with that? Okay. So we now have the whole balanced equation. Okay. You may not have needed it, but it's usually a good idea to go ahead and write out your equation right away. It can help kind of center you on the question. Even if you didn't need to use it, you now have kind of focused in on what's happening. Okay? We need to know what?
Moles of sodium, hydrogen, carbonate.
Moles of sodium hydrogen carbonate. What am I starting with? Okay. 2 moles of sodium carbonate. Oh, but I also started with 2 moles of water plus 1 mole of CO2, so I just add that up and I get 5, right? Oh, I add that up, it does equal 5, but it makes no sense as far as the equation goes. Okay? So what we have to do is convert our moles of sodium carbonate into moles of sodium hydrogen carbonate. What is that answer? 1 mole of sodium hydrogen carbonate is, that would be 2 moles of sodium hydrogen carbonate. Let's try that again. Is 1 mole of sodium carbonate. Those numbers came from the Jake. Our balanced reaction equation. And the answer that we would get would be 4. So notice, we've already given 2 answers. I said 5. We just add up all the numbers. Said, oh, that was a horrible idea. You can't do that. 4. I mean, I got 4. Why is that wrong? I don't know if it's the limiting reactant. Okay, so in this kind of situation, I have to determine what the limiting reactant is. So I'll go through and calculate moles of water. 2 moles of H2O. How many moles of sodium hydrogen carbonate could be produced? Well, moles H2O, sodium hydrogen carbonate, 2 to 1, right?
Okay, yeah.
And we get an answer of 4. 4 is looking mighty nice.
But harder than last one.
And unfortunately, it's the wrong answer. Because when we move to the last one, 1 mole of CO2 needs to convert into moles of sodium hydrogen carbonate. Mole sodium hydrogen carbonate. Still 2 to 1, right? And we get an answer of 2 moles. Okay, so my answer is actually 10 moles of sodium hydrogen carbonate. Why is that wrong? Okay, I am limited to 2 moles. I don't add up all of the results because those were the maximum I could make starting with that original. Okay, so 10 makes absolutely no sense. Okay, just because you can add 4 and 4 and 2 and that equals 10 doesn't make that the correct answer. You have to interpret what they mean. Our answer then needs to be 2 moles. We end up with A. 4 moles was incorrect. Interestingly enough, I was actually somewhat nice in this question because
You can just use the equation, like the molar ratio, and you have one, like it's all 1 to 1 to 1 to 2. So you have 1 as part of that.
so if you're really good and you've had enough practice, you can do the mole conversions in your head and jump to 442. Is that what you're saying? Okay. So if you were awesome with doing it in your head, you could have gotten to the answer really quickly. We also did this in class. So if you remembered from when we did it in class, you had the answer. Okay. Why else was it nice? What answer did not show up? 10.
Yeah, that's fine.
10 wasn't an answer that showed up on there. Okay. So some of the wrong answers are way wrong. Like 0.5. Ooh, that one's actually not all that horribly bad. Or nice, I mean. What's the issue with 0.5? You screwed up your mole ratio, likely because you did what? Did the calculation in your head. Okay? So write the work down. Yes, it takes time. And if you see a question like this, you know it takes time, so don't do it right away. Move on, come back to it later. Make sense? So our answer, just because we talked a whole bunch about different answers, was our 2 moles. Okay? Does that make sense? Okay, so lots of work. Next.
Number 12.
I heard a 30 and then a 12. And actually in 30, I thought we talked about it. Maybe we didn't talk about it now. Now I'm kind of wondering about it. 30 is a Dalton's law. Does that ring in any bells? Dalton's law says that our pressure total equals, what's that? The added pressure of all the parts. That was Dalton's law. There's for sure a slide on it. I may have just hit it and said that's it and just move on. Okay, so you just add up the pressures to get your total. Okay. The question is, where are we within what information is provided? So oxygen gas is collected over water at 25 degrees Celsius and 775 torr. What is that 775? Yes, it's a pressure. Pressure of what? Oxygen gas is collected over water at a pressure of 775 torr.
So oxygen gas.
Could just be the oxygen gas, but then what's the rest of the question say? The vapor pressure of the water is 23.8 torr. What does that mean? So what we've got is our pressure total equals the pressure of our oxygen plus the pressure of our water. What values are we given? Or what values do we need to solve for? Let's try that first. We want the pressure of our oxygen, which means what information must we be given? The pressure total and the pressure of the water. What's the pressure of the water? It is 23.8. Water happens to be what phase? A liquid. What do some liquids do? Turn into gases. That's why we get evaporation. That process is known as the vapor pressure. Okay? So our 23.8 is corresponding to the water. So what is our total pressure then? That's our 775. So what do we do? Subtract, and we have our pressure total. Make sense? So yeah, a question can shuffle numbers all over the place and make it look like a mess. And if we look at our answer choices, what answer choices show up? 23.8. Sweet, that was given to us. Right? 775. Sweet, that was also given to us. What else do we have? 750 and 751. What do you think is being asked for there? It's probably a sig fig thing. And then 799. How do we get 799? We added them. What did we need to do? Subtract them. So again, just random combination of numbers will very often lead you to the wrong answer. So what does that come out to? 750.2? $751.2. So our answer is 751. Yeah, because how many sig figs are we allowed to use? 3, because 775 and 23.8 are all both 3 sig figs. Isn't 25 degrees Celsius only 2? I didn't do any calculations with it, so I don't care about it. Okay? Make sense? Okay. I believe the next one was 12. Starting with number, student makes number, calculated mass is number, what is the percent yield? How do we calculate percent yield? It's our actual over our theoretical times 100, which I'm going to ignore for the moment, which is the same thing as our experimental. That says experimental. Over calculated. And now I'll drop in the times 100. What information are we given? A student makes 1.75 grams of aspirin. What is that? That is our actual or our experimental. So 1.75 grams of aspirin divided by 1.88 grams of aspirin. Oh, this one isn't that bad. Sorry. No, I thought there was something else weird with it, but it's not there. So our experimental over our actual, punch that in, a whole bunch of numbers that are really close to each other, so I wouldn't be able to figure out what that was. Come out with C. Yes?
You don't even care about the top one, the 1.56?
So when we look at this question, let's change it up a little bit to the parts that we used. Whoops. A student makes 1.75 grams of aspirin. If the calculated mass of aspirin is 1.88 grams, what is the percent yield? How many different multiple choice answers would I be able to come up with? 2. How many multiple choice answers do I need? I need 5. Because I need 4 wrong answers, A, B, C, D, E. Well, if there's only 2 possibles with that sequence of numbers, what do I need to do? Add another number. Now, if you don't know what you're doing, you punch in the 1.56 as useless information, you will get one of those other answers. Does that make sense? So when we go through to calculate, this is where units can come in handy. The 1.75 grams was of aspirin. The calculated mass of aspirin is 1.88 grams, which means when we go through to calculate, the grams of aspirin cancel. If I'd used the 1.56, would that cancel? No. This is why you use the full unit, both the measurement and the substance. That can help you not use bad information. Okay. The other thing to watch out for, could you have an answer that was above 100%? Yes. That is allowed. It's bad experimentally, but we could explain why it happened. When you punch stuff into your calculator to calculate it and you get a number above 100, it's not a bad idea to check your work. But if you trust your work, it's fine to be above 100. Okay? Questions? 15? What? Why is someone saying, ooh, yeah? Makes me nervous. $15, I'm a little on the fence on, because I think we kind of talked about it and kind of didn't.
You should put on the test then.
I would argue that you have the ability to do it all the way. The other part of it is, since you've now asked it, I now know for sure that we have the ability to answer it. Sodium bromide dissolves in water.
I need to do more of those.
Sodium bromide. Well, they gave me the formula, NaBr. What kind of compound is that? All except aqueous. Yeah? If it's aqueous, what happens? What does it mean when it dissolves in water? Yep. What was that? No, don't quite accept that. I think I heard somebody else say it. Ions. We have an ionic compound, soluble in water, that splits into the ions. So really when we're looking at sodium bromide aqueous, it's not sodium bromide aqueous, it's sodium ion that is aqueous and bromide ion that is aqueous. Why was the sodium written as positive and the bromide written as negative?
Positive charge.
Sodium carries a positive charge, bromide carries a negative charge, and we know that because you memorized it from the periodic table. Okay? Those are important charges to have nailed down. That simplifies your work. Okay? Okay. Which of the following is formed in an aqueous solution? Okay. Well, in those answer choices, none of them just say sodium ion and bromide. They're showing the sodium ion and the bromide reacting or interacting with water. Okay, so let's draw out water. What is the structure of water? We have oxygen, we have hydrogen. We do our Lewis structure, we'd have lone pair electrons there. Okay. We had a suggestion that what happens when it hits water is that it needs to neutralize. We're trying to neutralize the charges. How do I neutralize a positive charge? With a negative. Do I have a negative in water? Sort of. Okay. I have a partial negative because oxygen is more electronegative than hydrogen, which means I get a very large partial negative on the oxygen and I get a partial positive on the hydrogen. That means, given the choice for my interactions, I would expect the sodium to interact with the oxygen part of water and the bromide to interact with the hydrogen part of water. Answer choice A shows the sodium positive interacting with hydrogen, which happens to be positive. What happens when a positive gets near to a positive? Repels. That's a bad answer. Answer choice B. The positive sodium gets near the partial negative oxygen. That seems pretty legitimate. Bromide negative gets near the oxygen negative. Repel. So A and C are wrong, which then means D is wrong, and it always sucks when you see none of the above. I mean, that's true, it does. You have to go back and look. You have a positive next to a negative. That interaction is favorable. That one's true. B is your answer. Okay. So it goes back to trying to establish partial charges and apply those partial charges to neutralize out. Make sense?
14.
Oh, we could have gone really fun with that. Galactose? Yeah, sorry. Just started to process some of the comic book stuff that could come out of this. Common name for galactose is cerebrose, or brain sugar. What is the molecular formula of galactose if the empirical formula is CH2O and the approximate molar mass is 130?
You're right, that was organic chemistry, sugar-like body.
Yeah, from a rain? Oh, cool. So maybe I didn't make it up. So before we get too far into it, what is the relationship between our empirical formula and our molecular formula? What did you say? There's a direct relationship. I like that. I want a little bit more. What did you say?
Whole number multiply.
Whole number multipliers. Okay. The molecular formula is a whole number multiplier from our empirical formula. So with that information alone, A is wrong. C is wrong. E is wrong.
What was the information that made all this wrong?
We did no work. Okay. The empirical formula versus the molecular formula. The molecular formula is a whole number multiplier or multiple of the empirical formula. Okay. So the empirical formula is the reduced ratio of the molecular via a whole number. So CHOA can't be right because that doesn't maintain the ratio shown in the empirical. C can't be right because that doesn't maintain the ratio. Okay? I scaled up just the oxygens but didn't touch the carbon and hydrogen. That's not maintaining the ratio. E, same issue. I've scaled up some of them but not all of them back to that ratio. So those answers are wrong. That leaves two answers as a possibility. B, saying it's exactly the same, or D. The odds that it's exactly the same are pretty slim. So we could just go straight to D. Okay. That's pretty amazing for doing absolutely no work. Okay. So having some understanding of chemistry can help you eliminate a lot of answers. Let's actually go through and solve this. How do we determine it? We need the empirical formula's weight. Carbon weighs 12, hydrogen weighs 1, but there's 2 of them. Oxygen weighs
30.
Seriously?
Yep.
Damn. Okay, 30. Oh, did you do this because you remember it?
Yeah, we did it yesterday.
I really don't know when I did it 2 days ago.
I was like, wow, you're doing math really fast. Okay. Can B possibly be correct? The molar mass of the compound is 180 grams. The mass of the empirical formula is 30. They don't match. B cannot be correct. I don't even have to solve any more beyond that. Okay? Officially, what we're supposed to do is take the molar mass of our molecular compound, divide by the empirical formula mass, and we get 6. We take that number and we multiply all of our subscripts in our formula. So it's C 1 times 6, H 2 times 6, O 1 times 6, and I get C6, H 12, O6. Oh, look at that. After all that work, we got the exact same answer as doing nothing. Okay. So being able to process and understand the material allows you lots of shortcuts. If you don't understand the material, you have to understand the process, which means you have to memorize that process. Okay? Next. So 29, what is the term for a gas that deviates from ideal behavior under conditions of low temperature and high pressure? The low temperature and high pressure are really just kind of confusing things. We're just saying, what is the term for a gas that is not ideal? It's real. That's all it is. Yep. I definitely, when we talked about this last semester, I talked about it a lot more in depth than we did this time. I'm starting to wean out the gas law stuff out of content because it's not required. Okay. So, yeah. I think I heard A. A?
No, for A, I just need a conversion if you don't want to go through it because I know it does a lot. I think that's super easy. I just don't know what conversion it is for the dozens aspect of it.
A is actually a tricky question that a lot of people get wrong. I've actually stumped tutors with it. And it's largely because you just are trying to overexert, I guess, on what's going on here.
Yeah, I think I'm just over.
What is our answer? What units of our answer do we want? Dozens, which I'm going to abbreviate DZNS, of CO2 molecules, MLCS. What are we starting with? Is moles of CO2 the same thing as dozens of molecules? No. Okay, so let's convert to something. What do we want to convert to? I would convert to molecules. Yeah, we're going to want to convert to molecules first because otherwise we'd have dozens of moles that we'd have to deal with, and that's going to be a mess to deal with. I think. So moles of CO2 to molecules of CO2. What is our conversion factor between those?
Is it that 6.022 times 10 to the 10?
6.022 times 10 to the 23rd molecules is 1 mole. What unit do I now have? Molecules of CO2. Is molecules the same thing? Molecules of CO2 the same thing as dozens of molecules? No, so what can I do? I want molecules to disappear and I want dozens of molecules to appear. What is the relationship between dozens of something and something else? There are 12 molecules in 1 dozen. What happens? You go straight across and you got your answer.
Thank you.
And I'm not, if you convert to dozens right out of the gate, it might still work. It should theoretically still work. But this for sure comes out cleaner, at least as far as I can see in my head. So if you did it another way, talk to me after class so we can clarify that. Okay? And then I think I heard 4, because we're running out of time fast. Good. This one I think is hilarious because I think tutors get a little ahead of themselves sometimes. I get a little ahead of myself sometimes too, so it's not just them. And they go through and start doing things by taking shortcuts, i.e. not showing their units. And they get the answer wrong, and then it's hilarious. Well, for me. So which of the following is 1 mole of the specified substance? What is the specified substance in each of those statements? Oxygen atoms. Okay. Oxygen atoms in 1 mole of carbonate. Oh, it says 1 mole, so that must be the answer. What is carbonate? CO3, technically minus 2. So if I'm given 1.00 moles of carbonate, how many moles of oxygen atoms are present? Mole of carbonate, moles of oxygen. What's the conversion? 3 moles, 1 mole. Is answer A true? No. Where did I get the 3 from? Someone want to help out? It comes from your formula of carbonate. It's not obvious. It takes practice to recognize where they are. Okay. So A is now wrong because there's 3 moles of oxygen, not 1. What about sulfate? What's our formula for sulfate? SO4 minus 2. Are we going to have 1 mole of oxygen atoms there? Nope. Carbonate shows up again, but this time 1/3 of a mole. 0.33. If we subtly change that real quickly, 0.333 moles times 3 equals 1 mole. 0.9999, which takes you to 1 mole. And actually I said it's 2 sig figs, so it takes you to 0.999, but I said 2 sig figs, so 1. So your answer for that is C. Lesson from that, show your units. Use them, they help. Okay? And with that, we're done. If you still have questions, you can come ask.